We're back. We had a power.
Joe, welcome back.
Are you with us again?
Huh?
Are you with us again?
I think so. I can see you.
Okay. And I can even hear you now.
What a
Just
deal.
messed up the recording. Maybe I can go edit it and put them together. I did learn how to do that once. Let's see if we can get back to where we were. Okay. Come on. Oh, it's already recording. Okay. Okay. All right. Like I was about to say, the AB of a little hybrid where they changed the biasing so that, and normally it's a push-pull type of arrangement. So the second transistor or tube is conducting for a small portion of the other cycle. So you don't, in the class B, it's linear up to the point where you change polarity and you get crossover distortion, particularly in a transistor amplifier because of, remember the threshold voltage of silicon? Well, you lose conduction at that point at the crossover. So AB was designed to take care of that. So it actually has both transistors or tubes conducting for a small period of time. And it also eliminates doesn't necessarily eliminate, it reduces the second order harmonics that you might have. So that's why you basically never see a B anymore. It's either an A or an AB or a C if it's, well, FM, C's fine. I guess it would work for CW. You don't necessarily care that the amplitude isn't linear.
Let's see, it looks like it's just
Pulse.
higher bias.
Yeah, it's less than 180 degrees. So you're essentially getting a positive pulse into a tuned circuit. So it's keeping it oscillating.
40%.
What?
40%.
Yeah. It's more efficient, but it's not linear. And then neutralization is just where you add some circuitry to provide negative feedback to compensate for any positive feedback you might have. Because the old saying was, if you want to build an oscillator, you build an amplifier. And more than likely, to get the gain up, it will oscillate. So a class A is typically around 25% efficient. This is showing a typical transistor class A circuit where you're biasing the operation at essentially the midpoint between saturation and cutoff. And you assume that you have a tube or transistor that has fairly linear transconductance. In other words, constant gain on its range, which isn't true. So if you look at the plots for a transistor, for instance, where they'll show increments of base current and what the collector current is, and the spacing of those won't be even because the transconductance changes a little bit. So it gives you some nonlinearity in the amplification. usually compressing the positive peak more than the negative. And if you go to a push-pull arrangement, that was one of the reasons to do that, because then you get that effect on both halves. So it's closer to being linear. The main thing is it's the most linear and it preserves the input waveform as much as possible. So what percentage of time does a Class A conduct, percentage-wise?
100.
You think they want you to go towards alpha and they mean something else? Sometimes they do that, but in this case, but remember, you're biased in the middle. So with zero input, you're half power. Okay, and you're either increasing or decreasing. So it's always conducting. That's why it's inefficient. Because if you have no signal, it's consuming power. What's the operating point of a Class A common emitter amplifier?
Alpha. Let's see.
This is not hard.
Halfway.
I know.
Saturation and cutoff.
Alpha, halfway between saturation and cutoff. To get the maximum swing. Now, if you wanted to, do it for maximum linearity, you might shift it one way or the other, depending on the characteristic of the device, and maybe not do the full swing. A Class B is normally a push-pull amplifier, so you have two devices, and one is conducting on one half of the cycle and one on the other. But you do have that crossover distortion problem, where, as you mentioned before, at zero, okay, it's not conducting in that threshold region.
Why is this one more efficient?
Because with zero signal, neither one is conducting. The top one is only on during the positive half of the cycle. Okay, and it's at cutoff when you get zero signal. And then when you go negative, you turn the other one on. That's why they call it push-pull.
Do you think that would be really about as efficient as you could get?
But you got the crossover distortion, which you don't have in a Class A.
Well, have we talked about that crossover distortion and that was missed it?
Well, yeah, I just talked about it.
Yeah, but what causes the crossover distortion?
It's a transistor,
Oh, the
base emitter. Because when the signal coming in is less than assume it's a silicon device, when it's less than 0.7, you're not going to conduct. Which is, when you look at the AB, okay, what they've done is add some biasing diodes to offset that. And it actually causes it to conduct partly on the other cycle. So you actually have both devices conducting slightly beyond their
So the class B, you have a little hole
right.
between,
That diagram didn't show it very well, but right, there's a little spot where you lost signal. It's not, and it's not supposed to be zero yet.
and you're calling that
They
distortion.
call that crossover distortion. Yeah. And that can create some of the harmonics plus the
So how's that diode fix that?
you're creating a bias. Remember the voltage drop across this diode, okay, it's going to be 0.7. Okay, and it's between the base and the emitter. And the base and emitter needs 0.7 in order to conduct. Okay. So you're always biased on. When it, yeah, you have to get, slightly below that bias voltage in order to get back to zero, and that's why it's showing conducting on the other part of the cycle. See, normally this would just be a resistor, just a resistive divider to set the bias, and then you do a self bias. Well, maybe not in this push pull. Yeah. So the main thing is a push pull. It's higher efficiency. It's more linear than class B because you eliminated the crossover distortion. And in doing that, it reduces the even order harmonics. No, was there another bullet down there? No. So depending on how much this bias offset is, will determine how far it conducts on the other half of the cycle.
Move that little black thing there in the point there, so you can see the input. It's the same. All right, it's just the sign.
All right.
And become the effect.
And they're only showing one of the transistors on the output. So
Bob, technicality, this is an emitter follower type thing without gain. Are these circuits from the license manual, or are these some you contributed?
well, the ones you'll see in a minute are that the questions are about are from the license manual.
Well, this circuit is less than unity gain, roughly unity gain, but push pull is usually traditionally is applied to an amplifier that has gain.
Well, the point they were trying to show is the bias network
Yeah, okay.
and the fact that it's a push-pull operation. Yeah, I don't think the circuit would actually work as is.
It would work. It'd be the input signal would have to be biased above ground.
Yeah. If those diodes were germanium, it wouldn't really be AB amplifier.
No, unless you had germanium transistors.
Oh, yeah.
Or if you had gallium arsenide and then you might have too much. So for what portion of the signal cycle does each active element in a push-pull class AB amplifier conduct? In other words, each half of the a class C, okay, it's going to conduct less than 180 degrees. It's much higher efficiency. I don't know what causes the variation. Some things say it can be up to 90%. It seems a little high, but normally they'll say it's around 70 or 80. And essentially, you're pulsing that tuned circuit in the output and keeping it oscillating. So it's a tuned circuit, you know, narrow bandwidth, not a wide band amplifier. And like we said, you can use it for CW and FM. It doesn't work too well on single sideband or AM. Which of these classes of amplifiers has the highest efficiency of the four listed?
Delta.
For which of the following modes is a Class C power stage appropriate for amplifying a modulated signal?
Bravo.
How's the efficiency of an RF amplifier determined? It was on the first chart.
Alpha.
What's the purpose of neutralizing an amplifier?
Bravo.
Class D is essentially a switching device. So you're going to do a pulse width modulation depending on the amplitude of the input signal. And then you run that through a low pass filter, get all the stair steps out to reproduce a sine wave. So it obviously is not going to truly represent the input signal unless you did an awful lot of filtering to make it back into a pure sine wave. A high power amplification where I think mostly in audio. I mean, I don't think you're going to find devices that you can operate that way in the gigahertz range. I don't know that I've ever come in contact with a D. Maybe Dan has some of his aircraft stuff. But it's on the exam, so you're supposed to know about it. But essentially, you know, it's highly efficient because you're operating as a switch, so it's either on or off. You're never in the intermediate zone, okay? You're either conducting fully or you're not conducting at all. And you conduct for a period of time proportional to the amplitude of the input. So you get this pulse width modulation waveform that you then have to filter or integrate back into a sine wave. Or doesn't necessarily, it's whatever it wasn't necessarily a sine wave coming in. Well, that's the way switching power supplies work too. Except you're trying to make it DC. Which of the following describes a linear amplifier? Probably should have moved this one up.
Bravo.
What is a Class D amplifier?
Alpha.
Why are switching amplifiers more efficient than linear amplifiers? Right. What circuit's required at the output of an RF switching amplifier?
B.
No.
Yeah.
Because all you got is a bunch of square waves, and square waves are full of what? Harmonics, right? Let's see. We kind of talked about that. You don't use class C for stuff where you need linearity or to preserve the input. And you don't want to use a class C because you can get all kinds of distortion, which could create excessive bandwidth because of the harmonics being generated. Let's see. We kind of talked about all that stuff. What can be done to prevent unwanted oscillations in an RF power amplifier?
Charlie.
Put ferrite beads and things on there and do negative feedback, which is what neutralizing does. Which of the following is a likely result when a Class C amplifier is used to amplify a single sideband phone signal?
Delta.
Okay, common emitter amplifier. Most typical circuit. This is actually a practical circuit that would work. So in this case, we have a voltage divider network, R1 and R2, which is going to set the bias voltage for that transistor. So it's going to be that ratio plus whatever your supply voltage is up there on the plus input. You've got another resistor R3, which provides what we call self-bias. Okay. So it's a little compensating one to help for linearity and things. And you notice there's a capacitor across it, C3. The purpose of that is it's a bypass for your RF signal because you want the bias voltage to be essentially DC. So you're going to basically maintain that as assuming the capacitor is the right size, a DC a self-bias voltage. So what type of amplifier circuit is figure E71?
Charlie.
Yep. Yes, Charlie.
Why do they call that common emitter? Because the emitter is essentially ground.
Yeah, and another stage it would be also ground. So in E71, what's the purpose of R1 and R2?
Voltage dividers.
Baker. Bias.
It should divide voltage divider.
What's the purpose of R3?
David.
Yeah, so. Full ground.
It's your self-bias, yes.
Okay. Another configuration is called an emitter follower or common collector. I guess it's common collector because multiple stages are all connected to the same point, the VCC. It's essentially used as a buffer amplifier where you're not looking for any voltage gain, but it's got low impedance output. So you've got current gain, you can drive a lot of circuitry. And for isolation as a buffer, like usually an oscillator, which doesn't have much drive at all without affecting the frequency, you use something like an emitter follower to isolate that from the next stage. Yes?
I'm trying to figure out what's the capacitor on input voltage.
I don't think. Oh, it's in the way. It's pretty straightforward circuit. You essentially put your load resistor in the emitter as opposed to putting it on the collector and take your output down there. So what's a characteristic of an emitter follower or common collector amplifier?
The input and output are in phase. Delta.
David,
Delta. They're in phase.
Whereas the common emitter gives you a phase reversal, 90, yeah, inverts it. Vacuum tube amplifiers. They're still around. You look at a catalog and half of the power amplifiers at least are still tube type.
Mm-hmm.
Huh?
You know why?
Why?
Oh, I was asking you.
Oh.
I got an idea, but
Well, from what I've seen, transistor ones for the same power cost more, which is a big reason, I think, because cost usually drives most things. I think they're more robust. It's harder to break a vacuum tube amplifier.
you can abuse the crap out of that.
Solid state, you can wreck in a hurry, and those MOSFETs are not cheap. But you do have to go through the, tuning capacitor and loading capacitor bit, which I guess that plus the glow, because
Right one. The space
yeah,
heater.
you get this nice, orange glow. And usually the output is a pi network. So you're adjusting the input and output capacitors in the pi network as the load and plate adjustments.
What determines the output impedance of a power amplifier? Or a power amplifier?
Well, basically the circuit and the transconductance of the device and the load resistance.
What I was getting at is the transistor.
Plus, in this case, you're going to have probably a pi circuit that, when it's tuned right, is going to be around 50 ohms.
Well, the transistor has a low impedance.
Right.
Yeah, well, tubes have high.
But if you notice, most transistor amplifiers, because you're operating them at relatively low voltages, are going to go through a step-up transformer.
Yeah. But
Tube amplifier, you're going to step down more than likely. Because for 100 watts, you need 70.7 volts into 50 ohms. And if you're running on 13.8, you got to step it up to get 70 volts.
okay. Let's move on. That's
It's back day one lesson there.
Yeah,
Okay, so we agree that there's probably more vacuum tube amps than solid state amps. I'd like to get that if they ever actually sell it, the ICOM IPW2, but
Yeah,
they got a new
it's
solid
about
state, I think it's
6,000
kilowatt,
bucks.
but it uses PDP. We'll talk about it when we talk about filters a little bit. Pre-distortion. So they compare the output, and some of the other manufacturers are doing a similar thing. You compare the output of the amplifier with a perfect wave, and then that difference you feed back and you modify the input to it to correct for whatever, up, down, whatever, in order to get a essentially perfect sine wave out without third order harmonics. It kind of works apparently, but it's complicated.
very, very processing intensive.
Yeah. So it's an SDR linear. Let's see. Yeah, and you do the tuning capacitor for minimum plate and the loading capacitor for maximum permissible plate current, short of turning them cherry red. So normally these are going to have a grounded grid configuration, which is shown here. And you notice the grid is going to ground, usually direct. Sometimes there's a little suppression thing in series, but essentially it's a circuit like this. So it's going to give you a very low input impedance and you're eventually going to match a 50 ohm output impedance. And you notice it's a step down transformer as shown because my Ameritron runs about 1600 volts, I think. He puts out 800 watts. So I'm not sure what that output voltage is, but it's probably only a couple hundred volts, if that. What's a characteristic of a grounded grid amplifier? Because you really want it to match the 50 ohm from your transceiver. Thermal runaway, if you got a transistor amplifier, is a problem because solid state using silicon, I'm not sure that the other semiconductors don't have the same problem, but silicon decreases resistance as the temperature goes up, where a normal conductor, the resistance increases as the temperature goes up. So because of that, you can get a situation where you have thermal runaway because the hotter it gets, the more current it can pass, that makes it hotter. And so you have to put some limiting resistors essentially in the circuit. And this kind of describes where the leakage current, causes part of the runaway. And normally it's just an emitter resistor, but that also decreases your gain and efficiency. Okay, you also have intermodulation products. If it's not perfectly linear, okay, you can get those intermodulation products, which are the result of mixing the different signals, and you get the sum and difference of this, the fundamental plus all the harmonics of those. And I think there's a chart here that's showing some of those. the main one to worry about is odd order, essentially the third order. Okay. It turns out that the third order harmonic is closer to the desired signal than the second and others, which doesn't seem intuitive. So if we look at one of these things where it's showing all of them, we have two signals, F1 and F2. So this is probably a result of, well, there's two signals you're receiving, or maybe you're doing a two-tone test, which is one way to check for these things. So you got the two different signals. Well, it turns out the third order intermod is going to be twice F1 minus F2 or twice F2 minus F1. So it turns out that those are very close to F1 and F2. Whereas your second orders are far enough away, they're fairly easy to filter. And the other third order is way out there and fairly easy to filter out. But the ones down here, very close, are hard to filter. So the higher they are, the stronger they are, the more interference it's going to cause.
Don't they normally quote those as being down 70 dB or something like that?
I'm not sure. I know that they've recently changed the FCC for third order. I think it's 43 dB down now. Used to be 35, I believe. And Baofeng UVR5s don't meet it. Surprise, surprise. Did you understand this chart since you were
No,
going to talk about it?
no.
Okay.
I'll try.
There's no question yet. It comes later, not today.
What's the chart still?
Intermodulation products. You've got F1 and F2 are your two signals, your fundamentals you care about. We won't talk about how they were generated. And then what all the intermodulation products would be for those. And if you notice, you've got two sets of third order, one way up here, okay, and one down here right next to it. And the reason these are important for later on is there is a question where you actually have to calculate 2 times F1 minus F2 or 2 times F2 minus F1. Because they'll give you some frequencies and stuff, and it's one of the hardest ones on the exam. Okay, so we talked about all the different classes of amplifiers and efficiency and neutralizing. We talked about biasing for common emitters and the difference in an emitter follower and a grounded grid vacuum tube and third order intermodulation products. Any questions on those?